So now we're going into chapter 7 and section 7.1, ratio and proportion. So now we're going to talk about shapes that are different from each other in size mainly. So they're still the same type of shape, but they're not identical, they're not congruent. We're going to get to do two shapes that are similar, so mostly the same, but not identical. We're going to start by talking about ratio and proportion. So how we compare two shapes to each other. So there are three main ways to write a ratio, and you want to be able to recognize these three. So A to B, actually you write it out with the word 2. A colon B, but we still just say A to B, just write it differently. And then a fraction, A over B. And what you can assume from these numbers is that A to B describes the size of A to the size of B. So for example, if A is bigger, let's say 3, and B is smaller, let's say 1, you can expect the ratio to be bigger on the A side and smaller on the B side. So you can assume those things when you're not given any specific numbers. Me personally, I like the fractions the most, I use those the most. And eventually we'll start making these ratios into long lists of ratios and usually setting them equal to each other, which is when we get a proportion. So a ratio is just one comparison, one fraction, one colon, one sentence with the word 2. A proportion is multiple ratios that are equal. So a comparison of two objects, a comparison of another two objects, but those comparisons are the same as each other. So we'll get eventually, and I like to use fractions, a fraction equaling a fraction. Now because these are two separate comparisons that are equal, and the comparisons could be A to B or B to A, so big to small or small to big. What I usually like to do is I usually like to make some consistency between the ratios. So I have one here, and how I'll organize the ratios is with the first one, I'll compare the big to the small. So if we're looking at this example, I would compare the A to the B, the big to the small, and then use that same comparison in the other ratio. So in the other ratio, also do big to small. And then I get that horizontal consistency. The bigs are on the top, the smalls are on the bottom. And then when we're looking at specific examples, we'll look for vertical consistency also. So are we working in one ratio vertically comparing to another ratio vertically? So as we get into these, there are some things you can do to simplify what you're doing and have some consistency between separate ratios. So let's say a single ratio compares more than two objects. So just got out of chapter 6, looking at quadrilaterals. What seems to be a rectangle, but we knew it to be a parallelogram because there are opposite congruent sides. A 3 and a 7, a 3 and a 7. So we could write all 4 as a ratio, just comparing them. So over here, 4 blanks, 3 colons, doing that comparison. And just like we talk about shapes, you go around the shape. So starting here, arbitrarily starting here, 3, let's go clockwise, 7, 3, 7. So a 3 to a 7 to a 3 to a 7. So a ratio doesn't have to be limited to only 2 quantities. You can do more depending on the information you have. So a pretty common example, looking at angles of a triangle, and you think about all the things you know about angles in a triangle. So the ratio of the angle measured in a triangle is 1 to 5 to 6. What is the measure of each angle? Well, from the Triangular Sum Theorem, you should know that all the angles add up. To 180 degrees. So the first angle plus the second plus the third. Now we know the ratio 1 to 5 to 6. So 1 of these, 5 of these, 6 of these. So 1 part, 5 parts, 6 parts. So now talk about that more algebraically. So 1 part or 1 unknown, 5 parts or 5 unknowns, 6 parts or 6 unknowns. And algebraically for unknowns, you know we use x. So 1x, 5 x's, 6 x's. So 1 part, 5 parts, 6 parts. All added up should equal 180. So 1 to 5 is 6, 6 and 6 is 12. So 12x equaling 180 degrees divided by 12. And x will equal, I think, 15. So 15 degrees is our part. So 1 of those 15 degrees, 5 of those 15 degrees, and 6 of those 15 degrees. So always answer the question that's being asked. What is the measure of each angle? So take your part, plug it back in. So we have 1 of those parts. We have 5 of those parts. Oh, made that worse. Okay. And then 6 of those parts, so 90. So 1 part, 5 parts, 6 parts, all adding up to 180, which you know from the Triangular Sum Theorem. Also in this section, looking at something you've seen before, so the cross product property. If you have a proportion, so 2 ratios that are equal to each other, then you can cross multiply. So A times D equaling B times C. So using that cross product property to set up and solve examples 2 and 3, look at those and then check your answers with my completed notes online.